Hey everyone, welcome to our video. We're going to be talking about partial pressure and then how gas laws relate to stoichiometry today. Like other videos, this one should tie into your D2L piece, so please make sure that you're following along with questions there so that you can kind of answer the things as we're going along. You'll find that to work much better. So we're going to be looking at partial pressure and gas laws. So we already talked a little bit about the ideal gas law and trying to determine pressures that exist within a system. We've already talked about the kinetic molecular theory of gases and how their movement cause pressure and all that good stuff. And so what we're going to do is we're going to really try to look at partial pressure and try to understand, well, what happens when we have mixtures of gases? So let's imagine that we have a container that has both CO2 and oxygen atoms or molecules in it. We know something about the volume of the container. We can see that it's 2.5 liters here. We know the temperature. We know how much each of the two gases there are. And so there's a couple different kinds of questions we could answer or be interested in. One is, what's the pressure of oxygen in the container? We might be interested in what's the pressure of CO2 in the container. We might be interested in, well, what's the total pressure? And so we should be able to answer all these things if we go to that ideal gas law, the PV equals nRT. So what I want you to do is take a few moments, pause the video, and then try to answer those questions on D2L, and then resume the video and we'll look at those answers a little bit. Okay, so hopefully you've had a chance to go and enter those things in D2L. So let's look at this a little bit. Let's address that first question. What's the pressure of oxygen in that container? Well, to do that, we're going to use our handy dandy PV equals nRT. We're going to rearrange that, right? So we've got the pressure of oxygen is going to be equal to nRT divided by volume. Again, sort of fixing that. We plug those values in, and hopefully you got an answer of 3.43 atmospheres to that. That'd be awesome if you did. We then might also want to try to answer that question of, well, what's the pressure of CO2 in the container? And so we would do that same process. We're going to obviously put a different value in there, so that's going to be 1.95 moles. We're going to get that, we've got 19.1 atmospheres in that case. Okay, so those are each pretty key. And one of the things you'll see as we think about that is in each of those cases, we're really just looking at the pressure of that gas without really considering any impact that the other one has. We might then also be curious, well, what's the total pressure? And so the easy answer is, well, let's just add those two things up, right? Let's take the total pressure. It's going to be the pressure of the oxygen plus the pressure of the CO2. That's going to give us 22.5 atmospheres. Now, you might have also gone about this a different direction, which you might have said, oh, well, I know how to find pressures of gases, so let me just find the pressure and use the total number of moles here. So add those two moles together and put it together, and you'll find that, hey, we get the same answer. And so you might be wondering, well, can we do either of these approaches? And it turns out the answer is yes. Either of those are going to work equally well. As you see here, we get to the same answer. And this gets at the idea of the partial pressure. Because again, remember, the pressure depends on the number of moles, not the types of gas. And so what that means is that our total pressure is just going to be the sum of those two individual pressures. The fact that they're different doesn't really make any difference because it's the total number of moles is the thing that's important here. And this is this idea is known as Dalton's law of partial pressures. And so you might see that appear somewhere. And so if we consider Dalton's law of partial pressures, that can be written some different ways. This is one way that it's often written. So it just says the total pressure is going to be equal to the sum of all the individual gases. As many as you have, they would just be additive. We can think about that, right? Though we know the total pressure should be equal to the total number of moles times RT divided by the volume. And that total number of moles, of course, is just going to be the sum of all the individual moles of the different gases. And so we can kind of break it out that way. And then you can do some distribution of our factor across the parentheses, right? So RT and divided by V could get clustered with each one of those n's. But of course, if we think about it, n sub A, so the number of moles of A that we have times RT over V is really just the pressure of A. And this would be the pressure of the B. And so we can sort of see how that might actually come about in a way that would make a lot of sense to us. So again, seeing it mathematically, it's like, oh yeah, that kind of works out. Another idea that sometimes comes up is this idea of mole fraction. And so this is a new idea. I'm just going to introduce it here. We'll use it a little bit more later on in the semester, but it's useful to kind of talk about it here, just to introduce it. And really what this goes back to the idea of our partial pressures, right? Our total pressure is equal to the pressure of A plus pressure of B plus pressure of C. This is sometimes represented another way, and so sometimes Dalton's law of partial pressures is written this way. Where we've got this P total is this X of A times P total, X of B times P total. And so you might be going, well, what is this X? That's actually mole fraction, and it's defined this way. So the mole fraction of A is this X of A. That is the moles of A divided by the total number of moles that we have. And really, if we think about it, all that is that's a decimal fraction of A. So what percent of the total number of moles are A? But let's do that in a decimal fraction. And so that's really useful because that's sometimes an easier thing to determine. So, and that just gets at this idea that, the percent of the total pressure of gas A is the same as its percent within the mixture, right? Because again, the total pressure that we have is just dependent on the number of moles, not what they are. So again, what they are isn't terribly important. And so again, we just got to introduce this idea of mole fraction right here. So you can see it, again, this will come up when we talk about solutions again. So another important thing to remember about gases, though, that's a little bit different than when we talk about solids and liquids, is that we can actually use volume as a counting unit for gases. And this happens because if we have a balloon, we've got 1 liter of CO2 at a particular temperature, and pressure, that's going to have the exact same number of moles as 1 liter of O2 does at that same temperature and pressure. And so what that means is volume often can be sort of used in place of moles when we're talking about gases. And so again, I really have to put that caveat on there. So if we're talking about gases, sometimes we'll have that. Now, if ever you're unsure, just always go to moles. That's always a safe way to do it, but it's nice to know that we can also use this as the counting. And the way that what that really means is that if we have some reaction, so let's say we've got CO that can react with H2 to form methanol, usually we would say, hey, that's 1 mole of carbon monoxide plus 2 moles of hydrogen gas gives us 1 mole of methanol. We can also, though, say, hey, that's 1 liter of CO2 plus 2 liters of H2. We'll give 1 liter of methanol. Again, they're all in the gas phase, so that works perfectly well, and they have to be at the same temperature and pressure. So that if we pay attention to those caveats, it can be a really useful little piece. One other thing just to note is sometimes they'll talk about standard temperature and pressure for gases. So the standard temperature and pressure is 1 atmosphere and 0 degrees Celsius, or 273 Kelvin. So again, just sort of a note there. We don't necessarily do a lot with it in this class, but you may see it if you're looking around the internet and you find some other things there. Okay, so let's look at reactions with gases. So really tying gases to stoichiometry. And really the idea we want to get at is how do we use the ideal gas law along with balanced chemical equations? And really the key here is that if we think about our balanced chemical equation, that's always talking about the number of moles typically. And so we can relate moles now to volume from the ideal gas law or to pressure, etc. So basically, if we think about stoichiometry, typically we would have the mass of A, we would convert that over and to figure out something about the number of moles of A that we have. Then using our chemical equation, we would then be able to convert this over into the moles of B. That could be a product, it could be another reactant, whatever we're looking for. And then we can use that and we could find, for example, the mass of B. That's frequently what we're looking for. However, the ideal gas law just simply gives us another way to be able to find moles. And so now if we're given pressure, volume, and temperature of A, that can allow us to also get to the amount of A that we have present. And then that would be able to, just like before, use the balanced equation to figure out how many moles of B we have. And then we could find the pressure, the volume, or and temperature. Or if we know the pressure, volume, and temperature, then we can find information about B. And so again, as we think about this, really PV equals nRT is often just another way to get 2 moles or to use moles to find some other interesting piece. So what volume is produced or other things like that. So if we think about our stoichiometry just a little bit here, we've already know that we can take the number of particles and we can get to moles. We can take the mass in grams, we can get to moles. We've been doing both of those quite a bit. Molarity sometimes we use to get to moles as well. Well, all we're really doing is we're just adding in one more way to be able to do that. We're adding in gas properties and using the PV equals nRT as a way to be able to do that. So let's see if we can take this for a little bit of a spin. So one way we could think about, or one place we might care about gases, would be if we're thinking about automobile airbags. These things will inflate, and this happens through this reaction that's shown down here, that we start with this solid, and it is actually going to produce a gas. Okay, so we can actually figure out, well, what volume of gas would be produced when this airbag goes off. And so if we've got an automobile airbag and it has a volume of 11.8 liters, well, how much sodium azide, that's this compound, needs to actually be in there in order to fully inflate this thing. And so we have to make some assumptions. It's probably reasonable to assume that we're going to have 1 atmosphere of pressure, and this would be pretty standard kind of room temperature-ish, about 25 degrees Celsius, so it's a warm, nice day. So let's see if you guys can actually figure that out and figure out how many moles, or how many grams, I'm sorry, of sodium azide we actually need here. So we're going to go to our ideal gas law, use the equation, and so let's have you pause the video, actually go answer that question on D2L, and then restart this once you're ready. Okay, hopefully you've gotten a chance to answer that on D2L. So let's sort of look through how we would do this. And so again, we've got our information hanging out here. We've got our volume, we've got our atmospheres, and we've got our temperature. So if we've got a volume, pressure, and temperature, that should be a good sign that we can probably use those to actually figure out the number of moles of N2 in this case, because that's our only gas that's present here. Because remember, only moles of gas go into the ideal gas law. It is the ideal gas law for a reason. And so again, we're going to use PV equals nRT to be able to make that conversion there. And then once we have that, we should be able to figure out the moles of sodium azide that we have because we have a balanced equation. Okay, so that's that link. And so we know we've got 2 moles of sodium azide for 3 moles of N2. And once we've done that, we should be able to get and then figure out our mass of sodium azide. And so hopefully you're looking at that. And so that's going to be using our formula way. So we have all the information here. So we can take our ideal gas law, rearrange it so that we can find moles as easily as possible. Again, just sort of always double check that to make sure it's right. This is one of the common things that I see students screw up is they'll flip that. Then we're going to put our assorted values in. And once we do that, we can figure out the number of moles of nitrogen that we have. Awesome. Now we have to do that second piece because that took us up to this point right here. Now we have to do these next 2 steps. So we're going to take those moles of nitrogen. We're going to multiply that by the balanced, the ratio from the balanced equation. We're going to multiply that by the formula, and that should get us to our final answer. So hopefully you got there. But if not, then you can sort of see where things might have gone astray. Now, I want you to think just for a few moments, like what would actually happen in this scenario if we had more sodium azide or if we had less sodium azide in there initially. And so take a few moments, answer these questions, and then answer the remaining ones on D2L. And that'll give you some practice sort of making the links here from gas laws into stoichiometry and also talking a little bit about partial pressure there.